dead in here. All right, 13.2 is where we finished up, or we stopped in the middle of 13.2 last time. We were doing things called line integrals, right? The last thing that we talked about was, can everyone see, or is it too bright in here? We're good? Okay, so that's the last problem we did, correct? So what we're trying to do, geometrically, we have a curve sitting in space somewhere, right, or sitting on the ground, and then we have some surface above it, and we're trying to find the area of the curtain drop down. That's the geometric interpretation of what we're doing. Now we have two other types of line integrals. The first one we learned about was the line integral with respect to arc length. We had that little ds at the end, which was our arc length. The other two types of line integrals are the line integral along the curve C with respect to x, which means that what we'll do is we'll still have this f of x, y here, and we'll still have c here, our curve that we're going to integrate over. But then instead of having ds, we write dx. And so that changes what this differential is here on the side. Instead of it being, what was it before? What was that part last class? It was square root of derivative of x squared, derivative plus derivative of y squared. Instead of that, it's just the derivative of x with respect to t. Right, so that's the line integral along c with respect to x. And then you have something similar, the line integral along c with respect to y. All you do is replace this right here with y prime. All right? So a lot of times, especially later on, we'll probably get to it today, those two different line integrals will appear together in the same problem. So if you want to do the line integral, let me take some of that space out of here. Oh, I can't. There we go. That's supposed to be a little bit closer together there. If you want to do the line integral along the curve C of p of x, y with respect to x, plus the line integral along C of q of x, y, so two different functions, dy, then you can add them together like this. So this is just notation, right? Notice, I guess what you need to see here is that this left side is very clean, makes sense. There's two different integrals, right? One with respect to x, one with respect to y. If we put these together, it's implied that that line integral applies to this one also. I mean, some people would argue, well, that just means integral of that, right? And then plus this. But the notation means this. Understand? Okay, so let's try and do this. Find the line integral along C. Oh, I know I brought my notes. Did I bring my notes? They're there. Of sine x dx plus cosine y dy, where C is the top half, not half, top half of the unit circle. There we go. Whoa. All right, so we have sine x dx. Now, I'm going to use that notation to split it up now. Is that fair to do it like that? That means the same exact thing as what's being asked. Now, C is the top half of the unit circle. So let me draw that over here. Top half of unit circle looks like this. And it's going from 1, 0 to negative 1, 0, which is here. So I'm going to draw a little arrow like that. Again, I said last class that the direction of this that we're going will become important in a little while. So I'm going to go ahead and start thinking that way right now. How can we draw this curve C? What's a good way to find a parametric representation of that curve? A parametric representation. What is that? Okay, we could use kind of like a polar. X would be what? just cosine, right? And we used t last time, right? So cosine t. Y would be sine t. And what's my restriction on t? 0 to pi. Everyone agree that these parametric equations with these restrictions on t would draw that curve C? Yes? All right, let's work with this first integral right here. Let's work with that one first. By definition, this is the line integral. It'll be from 0 to pi of sine of x, right? But what's x? Cosine t. And then dx, but what's dx? What's that really mean? Come over here, right? It's this right here, right? It's x prime with respect to t. So we're doing this right here, right? dx is really x prime with respect to t, dt. So I come back over here. What is x prime? I may as well throw it down over here. What is x prime on the right side here? Negative sine t, right? So I have here negative sine t dt, right? That will be that first integral. Shall we go ahead and compute that? And we'll come back and do the other one in a second. Let me take the negative completely out. We have 0 to pi sine. Oh, you know what? Let's leave the negative there. Sine cosine t negative sine t dt. Does everyone see the u substitution? Okay, right, u would be this. du is exactly right here. Everything, that's du. So this is really trying to take the antiderivative of sine of u. Antiderivative of sine u is what? Negative cosine u. So this will become negative cosine of what's u? Cosine t. And evaluate that from 0 pi, right? Pi 0, whatever. Let's plug in pi. What's cosine pi? -1. And then what's cosine of -1? Whatever it is, right? So this is negative cosine of -1. If you wanted to find out, I noticed this on a few of the take-home tests. If you wanted to figure out what cosine of -1 was and get an answer, then what would you do? Make sure you're in radian mode on your calculator. I noticed that some of you would do cosine -1, but you were in degree mode on your calculator, and that will give you an incorrect result. So make sure you are in radian if you're going to find that out as a decimal. Now what? Subtract from this what we get when we plug in 0. What's cosine 0? 1, right? So we get negative cosine 1. So this is negative cosine -1 plus cosine +1. Anything else you can do with that? What's the relationship between cosine of 1 and cosine of -1? Are they the same? There's an identity, remember, or a formula that cosine of x is equal to cosine of -x. Why? What do we call that when that's true? We call this what type of function? An even function. Cosine is an even function. So I could say that this piece right here is also cosine of 1. So what does this turn out to be? 0. Because I'm taking negative cosine of 1 plus cosine of 1, that's 0. So I get 0 from that? Agreed? Okay. That's just that first part of the line integral. Now I need to go do the other one. So I'm going to do this on the next page. This one right here. Now what are we going to need in order to do that? we're going to need y prime, right? So let's get y prime real quick. This cosine t, right? So let me set this up on the next page. Line integral over c cosine y dy. This turns into integral from 0 to pi cosine y, but what's y? Sine t. And then my y prime, we just said was cosine t dt. And that, again, is going to be a basic substitution. So u is sine t, here's du right there. So antiderivative cosine of u would just be sine u. So we want sine u, but what's u? Sine t, evaluated 0 to pi. What's sine of pi? 0. And then what's sine of 0? 0. So I get 0 minus, and then what's sine of 0? 0, and then 0 to get 0. So the whole damn thing is for nothing, right? Literally for nothing. Now, go back up. Look at the directions here. Look at the problem. It says what? C is the top half of the circle from 1 to 0, right? From 1, 0 to negative 1, 0, and then, that should say then, and the, or the line, it's okay. The line segment from negative 1, 0 to negative 2, 3. So all I've done is I've only integrated it over one part of C, right? Just the circle part. I still need to do it over the line segment. So imagine here, this is C. C should have actually extended negative 2, 3. 3 is up here. I have a line segment that goes here. Yeah? When I looked at the problem, I completely missed that. So I need to adjust some things here. For this to be technically kind of correct, why don't we call this circle part of it C1? Why don't we call this part of it C2? Is that fair? Call the circle part C1, this part C2. And now I need to come back in and just change some things here. Well, I guess I can keep it. Just keep in mind that all of this whole first page here, and this second page is just on C1, right? This one right here is just on C1. So let's do C2 now. On C2, that's my line segment that goes from here up to here, and it goes in that direction like that. How can I find parametric representation of that? Vector function, right? Line segment. So let's see if you remember R of t is equal to, we start with our initial point converted to a vector, which would be what? Negative 1, 0 plus t times the direction of the line, right? Which is the vector that connects this to this. So you subtract coordinates, what do you have? Negative 1, 3. Put those together. Negative 1 minus t, and then the other one is just 3t. And why did we do that? Because we get the parametric equations for x and y that way, right? X here would be what? What's x? Negative 1 minus t. Y I'll put down here. Y is 3t. Won't we need the derivatives here? May as well get them. What's x prime? Negative 1. Y prime? 3. And now we can go set up the integrals. Questions? So the line integral over C2 of sine x dx is turning out to be, oh, we didn't talk about restriction on t. Oops. What's the restriction on t? What will it always be if you do a line segment and you do it the way that I've shown you here? 0 to 1. You have to have that, right? You have to have your restriction. So 0 to 1. That gives you your limits of integration back here. 0 to 1. I'm doing sine of, okay, sine of what? X. What's x? Negative 1 minus t. And then dx, but dx is actually x prime, right? With respect to t, which was negative 1. And then dt. With me? What's the antiderivative of sine of negative 1 minus t? Antiderivative. You could do a u sub. If this is u, right, then that's du right there, isn't it? So I'm doing the antiderivative of sine of u, which is negative cosine u. So this should be negative cosine of u, but u is negative 1 minus t. Evaluate that from 0 to 1. Yeah, you'll wind up getting two negatives, right? Derivative cosine of something is negative sine, and then, yeah, okay. So plug in 1, what do we get when we plug in 1? Negative cosine of negative 2, and then when we take that, we subtract when we get what we get when we plug in 0. What do we get there? Negative cosine of negative 1. I could write this negative cosine 2 plus cosine 1. Is that a fair assessment of things here? Cosine of negative 2 is the same as cosine of 2. And then negative negative is positive, and then again cosine negative 1 is the same as cosine 1. That's good. That's some number. Am I done? Nope. I still need to do the line integral along C2 of that other part, which was with respect to y. So now, line integral along C2, it was cosine y dy. For us, that'll be what? Same thing, 0, 1. Cosine y, what's y? 3t. What is dy? 3. dt. Antiderivative is sine 3t. Evaluate 0 to 1. Plug in 1, you get sine 3. Plug in 0, you get 0. So you get sine 3. Questions? So what we have is final answer. Line integral over the entire thing, sine x dx plus cosine y dy was equal to, well, we had zeros from when we went over the circle, right? Top part of the circle, we got zeros for all that. Then we got, what was it, negative cosine 2 plus cosine 1 plus sine 3. Was that it? Okay. That's it. All right, now let's talk a little bit about these paths. Okay, so I have two paths labeled here. We have 2 points, A and B, right? And we have a path C, which goes from A to B. You see that? Path C goes from A along this curve to B. If we write instead of C, if we write negative C, what we mean is we change the path to go the other way. So notice negative c, as I move along in time, it goes backwards, right? So the negative in front of our curve doesn't mean like change the sign. It just means change the direction, all right? So what are some properties that we have? If you want to find the line integral along the curve c of some function with respect to x, okay, dx, then the relationship between that and going along the curve in the opposite direction is that you'll get the same answer, but it'll be negative, right? So you see, it changes the sign. Make sense? Same thing with respect to y. If you go with respect to y and you change the direction, then that means you just change the sign. Whatever this answer is, it's the same thing, just change sign. But if you do it with respect to arc length, it doesn't matter which way you go. Why do you think that is? Yeah, an arc length is always going to be a positive number, right? So it will not have an effect on anything. All right, so those are some relationships we may need later. And then we start talking about what's called path independence. Given 2 points A and B, what happens if we choose two different paths connecting them? Does it change the path of the value of the line, the path integral? What do you think? If I say do a line integral along C of some function, right? Do the line integral along C, and then I say do the line integral along C tilde, that's what that little squiggly is, C tilde, will you get the same answer if you're doing the line integral over the same function? What do you think? What's your instinct tell you? Think about it geometrically. Think about it geometrically. What did the line integral represent again? The area under the curtain, right? So if we go back to the beginning of this section and look at the area of that curtain right there, see? Would that area of that curtain be the same as the curtain that connects these two endpoints? So imagine the path went from 1 to -1 here, straight line, right? That would go up into the function, wouldn't it, somewhere? And then it would be an area underneath. Do you think that area would be the same as that one? What do you mean? Is what going to? Our curve goes here, right? And then those points get mapped up into this surface. It's kind of hard to see the surface there, but so if this line segment goes into this surface, up here somewhere you have the curve up here, right? And you're dropping from here straight down to this line. And you would get some area there. Is that going to be the same as the area on the outside? Could it be? For a certain function, like imagine that was just a flat plane up there. You could get things to work out the right way, right? Or you tilt it a certain way and it would work. But in general, the answer is no. Okay? In general, no. It is the value of the line integral depends on the path. What's that? Tricky? Okay. Does that make sense, though, that it wouldn't necessarily be the same? Okay. So path independence is what we're going to start to talk about, and what we're getting at is there might be a certain category of functions that the actual path doesn't matter. So like the line integral from A to B is independent of how I get to B. No matter how I do it, the value is always the same. And we're going to be very interested in those types of things. Let's see what I have here. So there we go. I don't know why I have that on there. Okay. All right, so check this out. What we're going to do is we're going to verify that it doesn't necessarily give you the same answer by looking at this line integral. We're going to do it along an arc of a parabola, and we're going to compare that to the line segment instead. In fact, I believe that arc, that's exactly this, okay? Was it? The point -5 to the point 0.02, is that what it says? We're going to compare going along here and then going along this parabola. And we're going to do it for some specific line integral. and we're going to show that you don't get the same answer. The paths matter. All right? Shall we? Let's do it. So let me write down the line integral along C, y squared dx plus x dy. All right, let's call this first one C, and let's do the parabola first. Okay, so C is this parabola. It goes from the point 0, 2 to the point negative 5, 3, negative 5, negative 3. It did something like this. Terrible. I can't draw it for my life. Good enough. Now, I'll draw an arrow. I'm going that way, right? Now, I gave you the equations here. It was x was 4 minus y squared, right? That was the equation of that parabola. What do we have to get in order to be able to do the line integral? What do we always have to convert our path into? Parametric equations, right? I need a parametric equation for a parabola. So what I need is, I need to be able to write my x as a function of t. I need to be able to write my y as a function of t, so that both the x-coordinate and y-coordinate are determined by a value of t, instead of, right now, x can be determined if I have y, right? So how do I do this? We want to make sure that we're using sine and cosine when we're dealing with circles. It works out great. When we have something like this, not necessarily. Y is equal to t. Why? Yeah, anytime you have an equation where one of the variables is solved for, that means x can be determined if I know y, right? So let's just say that y is t, right? If y is t, then don't you know what x is? And if I said y is t, then I can just let y be t, right? So, and then if it were the other way around, if this were solved for y instead of x, you would let x be t, and then y would be a function of t. So we will replace y with just t, and then x is exactly 4 minus, not y squared, but t squared. Now we do still have to figure out something here. What? Restrictions on our t, right? So where would t have to start in order to, remember, we need to start at this point up here, that initial point. So what would t need to be there? 2? Would that work? Plug in 2, what happens? You get 2 right here, you get 2, 4 minus 4 is 0, and then 2 here, you get 2, right? So you're at 0, 2, that works. All right, where do you think it's going to end? Isn't y your t value? T is your y value? The first point was up there too, right? Where's the second point? What's the y value down there? Negative 3. Let's just check to see if it works. Negative 3. What happens if we plug negative 3 into the top, into x? Negative 5, and you plug in negative 3 into y, you get negative 3. So that takes you to that last point. Got it? Sometimes it's just visual. Sometimes you have to really kind of think about this to figure out where these are. Oh, I have it backwards. Sorry, I can't have it that way. Oops. That's obviously a ridiculous statement. I'm glad you brought that up. We know the time is what? T must be at some point 2 and at some point negative 3. That'll give you the 2 endpoints. So I can't have any inequality that way because that makes no sense at all, right? So what's actually happening here? Which way are, if t is going to vary from -3 to 2, then what are we actually going to do along this path? We're going to go the other direction, right? Let me come up here and draw that in here. Like this, right? That's actually the direction we're going to go. Now, do the instructions say, doesn't say I have to go along a certain, oh no, it says, look, from -5, -3 to 0, 2, right? So that direction is okay, isn't it? That direction is what we wanted. What if we didn't want that direction, we wanted the other way? We would have to change it to the -c instead, and that would change our integrals. But for this problem, we don't have to worry about it. Okay, let's go for this. This is going to be c, this pad. So what do these two integrals become? The first one, integral from -3 to 2, right? And then y squared. Y squared is t squared. Then dx, but what's dx for us? It's the derivative of the x parameter, so parametric equation, which would be what? -2t? d what? t, right? With respect to time. Or with respect to t. That's that first integral. Why don't I throw that other one right here next to it? Plus, won't it be the same limits? Right? So, -3 to 2. What's x? 4 minus t squared. This time, what's dy? What's our derivative of y with respect to t? Just be 1. So that's just dt, right? Let me kind of clean this up. Can I make this all one integral? Could I? Yeah. This would be -2t cubed plus 4 minus t squared dt. And now, antiderivative, we have -1/2 t to the 4th plus 4t minus 1/3 t cubed, evaluated -3 and 2. So we get to plug those values in now, right? What do you get when we plug in 2? 2 to the 4th power, -8, right? Okay, got that? That's what we get when we plug in 2. How about when we plug in -3? What's -3 to the 4th power? 81. So -81/2. Okay, this right here, -12. This right here, 9. So we are at -8/3. And then we have what there? -3. Put those two together. What do you get? -8/3 plus what? 87/2. Put those two together. This is just tedious now, right? How do you all add fractions? Do you do common denominator? How many of you do like this times this, and then this times this, and then this times this across? Anyone do that? No? How many of you just do 2 on top, bottom here, 3 on top, bottom here? Okay. Different ways of doing it. 245/6. Sound good? Good enough. All right. All right, that is what we get line integral along C. Now what we want to do is the same exact problem. Compare that to the answer if we go straight line segment connecting these two. So this we'll call C tilde. Oh, that tilde is kind of extreme. All right, C tilde, and C tilde is going to go in that direction, from this point to that point. I'll do that on the next page. Give me the parametric for C tilde. Goes from -5, -3 to 0, 2. So C tilde, X is what? Y is what? So this, you do line segment, right? So you get the R, the vector equation of the line. Have we done enough of these now? Y'all agree? That should be the vector equation connecting those 2 points, the line segment there. T goes from where to where? In this case, 0 to 1, right? It's always 0 to 1 if we do it correctly. Are there any questions on that part? Okay, so X is going to be -5 plus 5t. Y is going to be -3 plus 5t. And then we'll need the derivatives, won't we? X prime is 5. Y prime is 5 also. Everybody ready to set it up? Okay, here it goes. The line integral from 0 to 1. Now I'll just write it up here. I'm doing y squared dx plus x dy, right? That's what we're trying to do. C tilde. That's what we're doing. So what is y squared? -3 plus 5t squared. Then times 5 dt, right? I'll save the dt till the very end. Plus, now let's do x, which for us is -5 plus 5t times dy, which is 5. And now all of that dt. Yay? Could you do that on your own? Yes? Should we not invest the time in class to do that? What I will do is I'll just give you the answer real quick. Where the hell am I? There they are. It's 0 to 1. It was it -5 plus 5t? -5 plus 5t, all of that squared, right, times 5 plus -3 plus 5t, but not squared, right, times 5. Where, right here? -3 here. The other one was just -5. dt. -5/6. If I typed it in all correctly there, it looks okay. That look all right? Is that the right integral? Okay, so negative 5, 6. So obviously, you don't get the same answer. So that just verifies that the path matters. All right, so that's what the next note says. In general, the line integral depends on the path. If we change the path, it's likely to the path integral will change. There are some conditions which makes the value of the line integral independent of the path we choose. We will address that soon, okay? It's called path independence. Okay, line integrals in space. So everything that we've been doing up to this point, we had the geometric representation of the area of the curtain as you drop it down, right? Because our curve, right, our C lived on the ground, and then we had the surface up above it, so we could map that curve up into the surface and then find that area. But what if our curve is no longer trapped in 2D? What if our curve is in 3D, and we're trying to find the line integral, so we're mapping that three-dimensional curve into a fourth dimension? We no longer have this area of curtain concept anymore. Know what I'm saying? But we can still define the line integral. So the line, we call this the line integral in space. The line integral in space will imply that we're in three-dimensional space instead of the plane. So the big difference is that earlier when we had the parametric equation for the curve C, it was x, right? We found the parametric equations for x and y. Since the curve's in 3 space, we'll have 3 parametric equations, x of t, y of t, z of t. We'll still have a restriction on t. And if you remember when we studied space curves, we could look at it as a vector, right? A vector function, where it has 3 components. So if we do this, then our line integral of f along C with respect to what here? With respect to what here? ds, what's that with respect to? When you see ds in a line integral, ds is with respect to arc length, right? So what's the arc length? This piece right here. Very similar to what we saw before, except we're adding in that third component there, that third piece. What does f of x of t, y of t, z of t mean? It means you replace all your x's with your parametric equation for x, all your y's with parametric equation of y, all your z's with parametric equation of z. Our limits of integration, right? A to b are restrictions on t. Everything is with respect to t, right? So another way we could write this is this way. Now there's something subtle happening here, so I want to make sure you catch this. Do we all agree with this part? If I ask you to find the magnitude of the derivative of r, well, here's r, right? What's its derivative? Well, derivative of each component, right? X prime, y prime, z prime. If I say the magnitude, you do what? Square root of each of those squared, right? So isn't this right here? That's just the magnitude of the derivative of the vector function. Yes? The only kind of weird part of this is f of r of t. You're taking a scalar function, right? Scalar function is a function like f of x, y, z. And I'm saying to plug what into it? A vector function. This is not technically, doesn't make sense. It's a notation thing. What we mean when we say take a scalar function and plug in a vector function is that you are replacing the x with the first component of the vector function, the y with the second component of the vector function, the z with the third component of the vector function. Understand? This is just the convention of the notation that we use to mean this. Understand? All right. We'll see that more. Okay, as before, we can also define, this time, 3 other line integrals. We can go with respect to x. So it's the same thing, except x prime at the end. With respect to y, same thing, except y prime at the end, instead of that big old square root ugly thing. And then with respect to z, which is z prime at the end, right? And then again, you can also split it up. If you have these three integrals, this is the notation we use for it. And so we can at least try one of these, right? Find the line integral along C of x squared dx plus y squared dy plus z squared dz, where C consists of the line segments from 0, 0, 0 to 1, 2, negative 1, and then from 1, 2, negative 1 to 3, 2, 0. How about this? I will do, this curve is actually 2 line segments, right? Why don't I do it just along one of those, and then you can finish it up the rest, okay? All right, so I'm just going to do the part that goes from 0, 0, 0 to 1, 2, negative 1. Does everyone see this is just an extension of what we just did already? Right? Okay. I'm only going to go from C, I'll call it C1 since there's another part of this we're supposed to do. 0, 0, 0 to 1, 2, negative 1. Now, I'm not going to try and draw that line segment because it's in three-dimensional space. And we already know that drawing in 3D is a little weird, right? So can you just tell me what the vector function is that draws that line segment? Well, where does it start? 0, 0, 0? What's the direction of that line? 1, 2, negative 1, right? It's nice. It was pretty convenient for us this time because we're starting at 0, 0, 0. So when we go and subtract these, we just get that vector. So this becomes what? T, 2t, negative t. So my x is t. My y is 2t. I'm going to draw it horizontally instead of vertically. My z is negative t. So these are my 3 component functions. I need derivatives of all those, don't I? X prime is 1. Y prime is 2. Z prime is negative 1. T went from where to where? 0, 1, right? Line segment. All right, here we go. I'm going to write all this in one line. Line integral is going to become integral from 0 to 1. X squared for us is t squared dx 1, okay, plus y squared, 2t squared, so 4t squared, and then dy, which is 2, and then plus z squared, so t squared, and then times negative 1, and then all that dt. And then you're off to the races. All right? Dot, 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 dot. All right. Now we get to something more interesting. Line integrals over vector fields. Okay, what we've been doing are line integrals over what? What have we been doing line integrals of? Let's see, go back here. Line integral along a C, right? Our C was a curve. That's it, right? We're doing a line integral along a curve. Now what we're looking at is a line integral over a vector field. Now, what was a vector field? We said that a vector field is like at every point in the space, there's a vector associated to that point, right? We did this in 13.1. You could say in two-dimensional space you have a vector at every point. You could say in three-dimensional space you have a vector at every point. Now what we're doing is we're going to do a line integral along a vector field or over a vector field. So watch, before we get to that, let's talk a little bit about something we talked about in chapter 10, which was this definition of this thing called work, right, which comes up in physics. Work is defined to be F dot D, the dot product of the force vector and the displacement vector. So if you apply a certain force and then you have a certain displacement, the work is going to be the dot product of those two vectors. Doesn't matter where those vectors are, right? You have a force vector and a displacement vector. You dot the two, you get some answer. That would represent your work. So imagine now you have a path, right? So you have this vector field sitting there, two-dimensional here, and you're trying to move along this path. So let me move along this path. I don't need that. Don't need that. See, my point there is moving along that path. At every point in that path, there is a red vector which comes from my vector field, capital F, right? So at that point, there is a vector. As I move around, that vector changes, depending on the vector field itself. And then I have this green vector, which is the tangential component of the curve. So if this blue curve is like an R of t, like a vector curve, right? Then this green thing is the tangential component, capital T, remember that? We can then look at this capital T vector as our displacement vector, and we can look at the red vector as the force vector. And if we dot the two, we get the work, don't we? And so what we're going to do is we're going to take like infinitesimally little tiny little segments and do the work on each one. Figure out the work at each infinitesimal little segment along this curve. And if we add all those up, right, all infinitely many of them, we get the total work required, or the total work done, to move a point along a curve through a vector field. Yes? So that's what I say here. Add them all up requires an integral, doesn't it? Integral to add things up forever. So what we can do is we can define the work. The work done at each point is that. Okay, add them all up, and we get the work is equal to the line integral over the curve C. But see, this time we're going through a vector field, so it's that the work is the force dotted with the tangential with respect to arc length. So R of t is what draws the curve. T is restricted between A and B. Capital T is the unit tangent vector. That's pretty much it. All right, that's what everything means in that integral. Any questions on it? No one ever asks me about this right there. ds capital T. Look, come back to this picture. If I'm saying that the work done at each point is the tangent dotted with the red, right? Didn't we say work, this green vector is the displacement? What's capital T? What's the length of capital T? Always 1. So I almost slid it by you there, that you let me say that the displacement on this infinitesimally small piece, that the displacement was 1. It couldn't be, right? It's an infinitesimal little piece. So how can I adjust that capital T to represent that infinitesimal? Multiplied by the little differential, the arc length there, right? The little ds. Which is why in the integral, right there, you have ds. This right here, this piece right here, is your unit tangent vector, which has length 1, scaled down to have a certain length. Well, what are you scaling it by? That infinitesimal differential ds. And so it's no longer unit length. Got it? This is like a scalar, and this is like your t. All right. Now, because of the way we define capital T back in whatever chapter that was, capital T was the derivative of r divided by its own length, right? And since ds, remember I just showed you this a second ago, ds was the square root of the sum of each of the derivative components squared, right? We said that that was the magnitude of r prime of t. Then if you take t and multiply by ds, right there, this t ds becomes there's t, there's ds, well, with the dt at the end of it. These two cancel, don't they? And so what you're left with is f dotted with what? The derivative of r. Now, what does this f of r of t mean again? Okay, so this is, remember, we had a second ago the scalar at r of t, right? Meant that we took the x, y, and z in the scalar and replaced it with the components of the vector function. This time what we're going to do is we're going to take the vector field and replace the x, y, and z in the vector field with the components of r. And then we dot those. So this is the cleanest version of the formula for work to work from. All right? That's it right there. So I put that down here. Note, is that in your notes? Is this thing at the very end in your notes? It's not there. I think I added that in last semester before I had printed that out. So just remember that that's what that means. F of r of t means you replace each component inside f. All right, let's see. And now the general definition. The one I have boxed, like I said, is the most important one. But this is just notation. If you ever see this, line integral along C of a vector field dotted with the tangential ds, that really means this. And if we take out the r of t, because we kind of know what that means, then this f is this. And then this right here, r prime of t dt, is dr. Notice the r has the vector symbol on it, right? This is the first time that we have an integral where our differential actually has a vector in the differential. That's different than ds, right? ds, that was an s vector. Okay. Also note that if you reverse the path, you get a change in sign for work. Find the work done by the gradient vector field of f of xy equals x plus y squared on a path traversing the top half of the unit circle in a counterclockwise direction. All right. So I want to know I want to find the work, right? So I want this integral. That's what I want, right? That's work. What I need in order to do this is I need to know what I need to know what f is. That's the vector field, right? I need to know what r is. What's r? I mean, like, f is the vector field, right? R is the what? The function that draws the path, right? So let's start with the path, because I think that's the easiest part. The path is the top half of the unit circle, counterclockwise direction. So how do I draw this path? You can do it like that, right? Counterclockwise. We've done that many times, haven't we? Now, before we would just say what? X is cosine t, y is sine t. Isn't that what we said before? This time I want to write it this way. R of t equals the vector function cosine t sine t. It's the same thing, right? If I give you this and I say, give me the parametric equations, you would give me those two. All I'm doing is I'm starting with what we've been doing, and I'm converting it back into the vector. What's our restriction on t here? 0 to pi. Now, if we go and look at the formula that we had here, in order to compute the line integral over this vector field, right, I'm going to need to know what r prime of t is, right? So should we just get that now? I'll put it here. Bless you. R prime of t is the vector, right? The vector negative sine t cosine t. Yeah? Now what do we need? I mean, are we pretty much done with r over here? Got all the information we need? Yeah? I need a vector field. Am I given a vector field? A vector field needs to be a vector, doesn't it? Like, I wasn't given a vector, I was given a scalar function. So how am I going to get a vector field from that? This right here, this is what was given. That's not a capital F. That's right. It says find the work done by the gradient vector field of a scalar function. Well, what's the gradient vector field of a scalar function? It's just the gradient, right? It's just the partial. So let me come back over here. I take the gradient of little f. The gradient of little f is what? So it's two pieces. It's the partial of f with respect to x, and then the partial of f with respect to y as in terms of components of a vector. What's the partial of f with respect to x? 2x plus y. What's the partial of f with respect to y? 2. Yeah, x plus y again. That's okay. Same thing. Right? Any questions on that? So this is capital F, isn't it? It is the gradient of the little f. It's the gradient vector field of f. All right, I'm ready to go and try and get this work computed. We're doing the integral over c f dot dr. We said that that's equal to integral over c of f of r of t, right, dotted with what? R prime t dt. That was the formula I had boxed, right? That was this one right here. Now, I should put a to b instead of over c. Sorry, let's change that. Even though I know what a and b are right now, I'm just going to put a, b. So let's plug into this formula. A to b for us is 0 to pi. What is my f when I replace my x's with what here? Cosine t, and I replace my y's with sine t. So I'm coming in and I'm grabbing the x component and the y component of r and plugging them into the vector field. So I'll have, is this still a vector? F is a vector, isn't it? So we have a vector. It is 2 times x, which was cosine t, plus y, which was sine t, That's the first component of f. Second component isn't exactly the same. Cosine t plus sine t. Close off that vector. Dot that with what? Negative sine t cosine t, and then dt. I now have to dot two vectors, right? Dot the vectors. How do you dot these vectors? Good old dot product, right? All you do is take the first component here, multiply times the first component there, add to that first component, or second with second. So I should get 0 to pi. What happens when I dot that first one there? Distribute it through. Let's go ahead and do all that at one time. I get negative 2 sine t cosine t, and then negative 2 sine squared t. That finishes the first part. Now I distribute the cosine through, so plus 2 cosine squared t, and then plus 2 sine t cosine t. All of that dt, which is going to cancel here. What about those middle two terms? We have that negative sign. That's a problem. If they were both plus, that would turn into something there, but they're not. Can I move off this page or keep it? Okay. So where are we here? We've got integral 0 to pi. I'm going to change the order. 2 cosine squared t minus 2 sine squared t dt. I don't like that. Let's pull the 2 out. How about that? Is there trig identity for that? But bigger question, can you integrate those or not? You could just do like a power reducing formula on both of those, couldn't you? In fact, that 2 might have been better just to leave there, right? If we power reduce that. That's the pre-cal identity, right? So you have different options here. Remember in pre-cal there was the formula for sine 2x was 2 sine x cosine x, right? But what's the identity for cosine 2x? There's a couple of them, right? There's 3 of them usually. One of them is what? And then what are the other 2? And then do I remember those? I mean, you may not remember them, but do you remember ever seeing those? Yeah, at some point in time. So we can actually replace that in there with what? Cosine 2t? Which might be the easiest, cleanest way to do it. So 2 integral 0 to pi cosine 2t dt. What's the antiderivative of cosine 2t? Sine 2t over 2, but won't that cancel with that 2 in front? So isn't this just sine 2t? Evaluate it from 0 to pi, and look what we get. 0. You have 0 total work. That doesn't mean that there wasn't work taking place at each point, but total work is 0. Is that all right? All right, find this where C is the parabola, y equals 1 plus x squared. So what time is it? 2:20? What is our next example, or is this the end? No, no. Pardon me? All right. How about this? It's 2:22. We're supposed to take our first break at 2:40. I'm going to give you the next 18 minutes to try and work this problem in groups together. Okay? Quiz. See how it goes. All right? You're trying to find the work done. You're given a vector field, and you're trying to move along this parabola. See if you can't grind this thing out. You think it's going to be 0? Well, maybe it is, but just work it out. I mean, well, for your total work to be 0, there has to be a couple of things that you would have to notice. You could have a symmetric path, like in this one, you have symmetry. But then also notice your vector field is symmetric too. That's why it'll work here. Just because your path is symmetric doesn't mean that you'll have total work 0, right? So the vector field, just put 0. That's it. Practice. See if you can confirm your intuition with the computation. Okay. So the vector field and the path have to be symmetric. Yeah, but in general, that might be hard to notice. You know. What's that? That's right. Sometimes you can't visualize what that is. This one you can kind of tell is symmetric, but okay. Go ahead. I'm going to pause my video, turn on the lights. So you should have wound up with integral -1 to 1 t over square root t squared plus 1 plus t squared squared, right? Plus, what was it? T plus 2t squared? Oh, it was 1 plus t squared? You already did the dot product there? What is it after the dot? 2t plus 2t cubed? Okay. Over the square root of the same thing, right? dt. And then if that's not something we can easily integrate, so. Well, on the second one you can, right? Yeah, but I think you're missing a t squared in there, so it would, your power would be 1 less, but you would have other terms in there. Look, we're not going to go through it. I mean, yeah, maybe not. I don't know. That's the most important part, is the setup. Okay? Anyone else need to sign in for quiz grade today? Yes? All right, let's take a look at the rest of the notes here for 13.2. So this is just another way of evaluating a line integral over a vector field. If your vector field f is PQR, so PQ and R are the component functions. P is the x component, Q is the y, and the R is the z component. Then when you dot f with dr, you get this. So what really happens here is that you're converting this vector function dotted with another vector function to a bunch of line integrals over curves with respect to x, y, and z instead. You see the difference? Sometimes it's useful to use that formula. Okay, this is not in your notes, but this is a problem I wanted to work through. A 180-pound man carrying a 20-pound tool bag walks up a helical staircase wrapped around a 20-foot radius cylindrical silo. If it takes 3 complete revolutions to reach the top of this 90-foot silo, then how much work is done against gravity? Note, work is measured in foot-pounds. Also, weight is a force. Okay, so you've got your man starting out at the bottom there, walking up around this silo in this spirally looking thing, right? We want to know how much work is done moving that guy up against gravity. Right, now, do we have a vector field? Gravity, right? Gravity is our vector field, and gravity, the vector field for gravity only points in one direction, right? We're going to consider it straight down in this case, even though technically it's towards the center of the Earth, but we're just going to say straight down is good enough for this approximation, all right? So we have force straight down, and then we have a path. Do we have a path? We do, right? That blue path. So let's see if we can put it together. So what is F? Zero, zero, and then the force of gravity straight down, right? What's the force of gravity on this man and his stuff? It's the weight. It's his weight, isn't it? Whatever his weight is, and he's carrying something, right? What did I say? He's carrying a 20-pound tool bag with him. So it's 200 pounds, right? 200 pounds. He's just carrying a tool bag. What's the sense of him walking up this thing if he's not going to go do something up there, right? So he's got the tool bag with him, all right? Or he could just be going up to jump off, right? to commit suicide. Compute the last amount of work he ever did against gravity. Is that our? Oh, 200. Thank you. About the what? Well, that's a great question. Do we have to account for gravity? Well, gravity is, how do we do this? The force of gravity, right, down is your weight. Your mass times the acceleration of gravity, right? Your mass times acceleration is your weight. With me? So his weight is the force. So you don't need the, 9.8 meters per second. You don't need any of that because his weight is the force. If they gave you mass, if they gave you the person's mass, then you would have to compute this. You would have to compute the weight. And then, of course, that would depend on what planet you're on and things like that. But his mass is not relevant in this problem. So that is the force of gravity straight down. Now the difficult part is R. So R was that coil spring-looking thing, right? And I'll bring the problem back up so you can kind of take a look at it again. The staircase wrapped around, it's a helical staircase, wrapped around a 20-foot radius cylindrical silo. It takes 3 complete revolutions to reach the top. So that means, let's look at it from, whoa, it doesn't want me to do that. Come on, man. Why can't I do it? There you go. From the top, what is it? It's just circle, right? Like in the XY plane, it's just a circle with radius 20, right? So I can say that my R of t is, what, 20 cosine t, 20 sine t? Agreed? And my T is going to go between where and where? I have to go 3 full revolutions, right? Which would be T is between 0 and 6 pi. I left out the last thing here, which is that last component of our vector function. That's the part that requires a little bit of thought. You cannot just put T here. Why not? Well, if you just put T there, I do agree it's going to go up as time goes on. But where are you going to wind up? How high are you going to be off the ground at the end of this? 6 pi, right? How high do you need to be off the ground? How tall is the silo? A 90-foot silo, right? So what you need is at the end, at 6 pi, you need to be 90 feet high, right? So could I do this? Could I say 90 T divided by 6 pi? How high would you be at time equals 0? 0. And this is linear, isn't it? Meaning that it's going up constant, right? This is the ratio in which I'm going up. It's like my slope, you could say. And if I plug in 6 pi, how high am I? They cancel, you get 90, right? I can actually simplify that. 6 goes into 90 how many times? 15. So I can say 15 over pi T. Does that make sense where I got that from? No questions? We have our vector field. We have our curve. So now we need some derivatives, right? And then we'll dot the 2, and then we'll have it. So my derivative is what? Negative 20 sine t. Is that really even going to matter? Is this really even going to matter, this part of it? What am I dotting it with later? 0, 0, right? Okay, but I'm still going to do it. Then what's the derivative of the last part? 15 over pi, right? And now I can compute it. It's 0 to 6 pi. We have the dot product of f dot dr, which is 0 to 6 pi. F is 0, 0, negative 200, and then dot that with negative 20 sine t, 20 cosine t, and finally 15 over pi dt. And that's just 0 to 6 pi, what? Negative 3,000 over pi dt. Take the antiderivative with respect to t, and you get negative 3,000 over pi t. Evaluate that 0 and 6 pi. So negative 18,000 what? Foot-pounds. Because you travel distance was feet and then the force pounds, so foot-pounds. Now, technically we could, well, I don't know. This is actually the work done by gravity. Because I mean, we're looking at you could look at it one of two ways. The vector field was either the gravity force or his force going up, right? If we looked at his force against gravity, then we would have used a positive 200, right, for him. Here we're looking at the force of gravity, which is negative. Either way, for him to get to the top, 1,800 foot-pounds is the computation of work. That was the work required, 1,800 foot-pounds. Okay? show you another one. We won't work through it. A 10-kilogram object moves with a position function. R of t is sine 4t sine 8t t squared, with t between 0 and 1. Find the work done on the object during this time period. So you've got this thing moving along this path, okay, in three-dimensional space. We want to compute the work. Can we use, well, the only thing that we would have to be concerned with here is the kilograms, right? Kilograms is not a force. That's a mass, right? So when we talk about force, we would have to convert over somehow times gravity, if that's what we're going to consider as the vector field. But that's to point out, like we said a second ago, just be careful in a problem like that. If you're given kilograms, that's mass. It's not your weight. If you're given weight, then you already have the force. Oh, I guess I at some point had wrote some code to compute the work done. You just type in the vector field, you type in the curve, and then it computes the work. All right, that's it for 13.2. 13.3. Bless you. So do you remember there's a couple of fundamental theorems in math. There's the fundamental theorem of calculus. Do you remember the fundamental theorem of calculus? There's two versions of it, but the one that most people remember is this one. Although there's another way of writing this. Right? The fundamental theorem of calculus basically gave us a way of connecting a derivative to its antiderivative, right? How the two were related to each other. We use the antiderivative to figure out the area under a curve, right? So that's one version of the fundamental theorem of calculus. There's also a fundamental theorem of algebra. Does anybody know the fundamental theorem of algebra? No? Fundamental theorem of algebra basically says if you have a polynomial of degree n, okay, so an nth degree polynomial, then there are n complex, that's, I'll say n zeros. Exactly n. N zeros. And I'll put it here underneath, might be complex numbers. So most people get through math without ever really getting presented with that, so they don't know it exists. So that's why I'm bringing it up to you. An example fundamental theorem of algebra. If I take a polynomial x squared plus 1, that's polynomial degree 2, right? There should be two zeros to that. The two zeros would be, well, I'd have to move over the negative 1, right? And then I get x equals plus or minus the square root of negative 1, which would be plus or minus I in this particular case, right? Two answers. Now, of course, if I change the problem to x squared minus 1, set that equal to 0, that's almost too easy, right? X plus or minus 1. Yes? But what about if I do this? X to the third minus 1. Set that to 0. X is 1. Do we all agree with that? There are two others. Pardon me? What? Other than, I'm setting them equal to 0? What? No? So these are polynomials, right? The fundamental theorem of algebra says that if you have a degree 2 polynomial, and you set it equal to 0, you should get exactly two answers. Degree 2 polynomial, I get exactly two answers. This is a degree 3 polynomial. I should get 3 answers. The other two are complex numbers. That won't work. This might be a way of. Have you ever seen the complex numbers system? We talked about this in the very beginning of class. That you can plot a complex number using a real axis and imaginary axis. When we just said x cubed was equal to 1, everyone was pretty much in agreement that 1 was an answer. Correct? 1 was an answer. Okay, the other ones will come from, what we need to do is we need to look the entire angle that goes from here to here is 2 pi, right? Divide that by 3, because we have 3 answers here. What's 2 pi divided by 3? 2 pi over 3? What angle is that? It's over here, right? And then over here, right? And then over here. Do you see those 3 points like this? See those 3 points like that? This point right here and this point right here, if you cube those will also give you 1. So let me try and figure out what this one is. What is the x-coordinate right here? What's the x-coordinate? Remember what this angle is. This angle here, so that's 120, which means this is 60 degrees. So negative 1/2, right? So the real part of that is negative 1/2. What's the imaginary part? That's the up part. Root 3 over 2, I. Now, if you haven't seen imaginary numbers, then this is just going to be confusing you perhaps. But I claim that if you take negative 1/2 plus root 3 over 2i, and you multiply it times itself 3 times, you'll get 1. You can do it on your own for an exercise. But the reason I used 1 is because if you have like if I say x to the 4th equal plus 1, if I set that equal to 0, how many answers should I get? I should get 4, and they will be exactly. We know 1's an answer, right? Now, what did I just say? Take 2 pi and cut it up into how many? 4. So these should also be answers. Check it for yourself. 1 to the 4th power is 1, right? Wait a minute, hold on. X. Hold on, I should get 4 here. X to the 4th equals negative 1, right? Get 45. Negative 1 works. Well, let me get back to this. What works for that? Negative 1? No. I. Yeah, we're going to have to go here, 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 and here. Did anyone do, what's this, pre-cal? This one? Yes. Yes. That is exactly what this is. And you can figure out what these roots are that way. I'm getting way off topic here, and I don't want to do that. The fundamental theorem of algebra says that a polynomial degree n has exactly n solutions. Some of them may be complex, some of them may not. period. The way you find them is a little bit tricky. That theorem that you had in pre-cal will do it. And I don't want to go any further than that. Take a complex variables class and you'll see more of that. Topology? No, sorry. Did you say topology? You're going to take a topology, or that's a good class. You might like that. It's not topography, right? Yeah, topology. Topology is really cool. All right, so let's get on to this. So we have fundamental theorem of algebra. We have fundamental theorem of calculus. Also, we have, oh, you know what? I don't want to leave that undone. Sorry. I can't leave this screwed up. I'm sorry. Let me do it this way, just to make it a little bit easier for us to. Do you agree that that has this? Right? Do we all agree that the two solutions here are 1 and -1? Okay, these two will also be solutions. I and -I will also be solutions. All right? If I do x to the 6th minus 1 equals 0, then I should have 6 of them. So x to the 6th equals 1. I should have, well, 1 and -1 work, right? But I'm supposed to cut up this 2 pi into 6 different 60 degrees, 60 degrees, so it should work here, right, here, here, and here. Any of those 6 points will also, if you raise them to the 6th power, you should get 1. Now, if I were to change this 1 to a 2 instead, there are also 6 answers to that, but they won't have length 1 anymore. If you're interested in this, just go Google what's called roots of unity. Roots of unity, and that'll start talking about the special cases when it's equal to 1. If you want to go past that, then it gets more complicated. So we now have what's called the fundamental theorem of line integrals. This is the next major result in the calculus sequence. So fundamental theorem of line integrals says, if C is a smooth curve given by some vector function, you got T restricted between A and B, and if F is differentiable function of 2 or 3 variables, so you can differentiate it, such that, and this is a big condition here, such that the gradient of F is continuous on C. Then the gradient of F, which is a vector field, right, dotted with dr. So this is kind of like, it's kind of like work, right? Except our capital F is a gradient vector field. Then this will just be this. What the hell is this? The original function, right? The original function, which was F, right? F. The original function evaluated where? What's R of B? Well, R is our curve, right? What's B? The endpoint of the curve, right? So you evaluate the original function at the endpoint of the curve. You subtract that from the original function at the starting point of the curve. Do you see the similarity between that? Yep, it's just an extension. Went past it. Of this one right here. Whoop, that. Right here, right? This was the derivative of something, right? This is the derivative of capital F, isn't it? The derivative of capital F, you want to do the integral from A to B of the derivative of capital F, then you just take capital F, evaluate at the endpoints. This one is saying, if you want to take the line integral of the derivative of F, right, derivative, gradient derivative, then all you have to do is evaluate the original function F at the 2 endpoints of the curve. Now it says, this theorem says the line integral of a conservative vector field is simply the difference of the value of the function at the endpoints. What was a conservative vector field? A vector field is called conservative if what? If it's the gradient of some scalar function. Okay, you have some capital F. If that capital F came from the gradient of some little f, then it's called conservative. But in this formula, this right here is the gradient of a scalar, right? So obviously that vector field has to be conservative because it's the gradient of a little f, which is what it means to be conservative. So if you take a conservative vector field and you want to find the line integral over that conservative vector field, all you have to do is evaluate the two endpoints. Further, the line integral on any two paths that connect the same 2 points are always equal. Why? Remember we were talking about two different paths, you get two different values for those line integrals? If we have this formula, if that is a conservative vector field, why does the path not matter as long as the paths go to the same two endpoints? If they start at the same point and end at the same point, why are we guaranteed to have the same value? Because all we're going to do to get the value of it is subtract the endpoints, right? So it won't matter how we got to the two endpoints. The fact that it's a conservative vector field guarantees that we'll get the same answer regardless of the path. But being a conservative vector field is a strong condition. You know, not every vector field is conservative. So we like conservative vector fields because of this. All right, let f of xy be x squared plus y squared, and c is given by that restriction on t is given. Find this. So we're given our scalar function, right? We're given our R of t. We're given our restriction on t. Now, let's try and make sense out of what this theorem is saying. Here's one option. Option A. If we're trying to find this, I could just figure out what the gradient of f is. What is the gradient of f? 2x, 2y, right? But be careful here. There's something a little subtle that we kind of missed there. That x and that y have to be replaced with what? With these two, right? Up there? But so I'm just going to leave them like this just for now, just so you can see how this is going to work. Times. Dotted with what? Derivative of r. So what's dr? You have to do some product rules on those, don't you? So sine t plus t cosine t, and then cosine t minus t sine t, or t sine t, dt. You following? But this is equal to line integral. We're going to go from 0 to pi. Let's plug in 2x. So that's 2t sine t, 2t cosine t. We're going to dot that with sine t plus t cosine t. Do you see this is not very good? Now what's wrong with option 1 here? I mean, this is not a fun thing to have to look at, right? I've got to dot that, I've got to do that times that times that, and then I have to integrate it, don't I? I've totally overlooked the fundamental theorem of calculus, right? Or fundamental theorem of line integrals. Fundamental theorem of line integrals says that if you've got the gradient of f there and you're dotting it with dr, you don't have to do any of this work, okay? You don't have to. All you have to do, so this would be option B, would be just to figure out what f of r of b is and subtract f of r of a. And you're done. So what's f of r of b? Well, what's r of b? Remember what a and b are, right? A is 0, b is pi. What's r of b? So f of r of pi minus f of r of, it was 0, right? What's r of pi? It's a vector, right? What is it? If I plug in pi, though, I get 0 here, don't I? And then if I plug in pi here, I get what? Negative pi. Right? Now I'm plugging that into this function. We said earlier, it's just a notation thing. We're going to plug a vector into a function. That just means I'm going to replace x with 0 and y with negative pi. Subtract from that what? F of, well, when we plug in 0 into r, we get the vector 0, 0, don't we? What did the f function do? X squared plus y squared, right? X squared plus y squared. So all I have to do now is do the 0 squared, right? X squared plus y squared. So that's just what? Pi squared, and then the other one? Minus 0, so we just get pi squared. See that? That took us, what, about 30 seconds, maybe? A minute to do it that way? What would have happened had we distributed up here? Look at that. That would have taken forever, wouldn't it? Because we would have done this. Look at this first one right here. 2t sine t times sine t will give us 2t sine squared t. And then here we would have, what, 2t squared sine t cosine t. Then we would have added all that crap. Maybe some stuff would have canceled, but it still would have been a lot of trig stuff to integrate, right? Along with t's stuck in front of them too. So there might be some integration by parts. And we've seen that with integration by parts with trig functions, sometimes you have to do integration by parts where you get the same integral to appear on the other side and you move it over. Remember that? That would probably have happened in that problem too. It just would have been a freaking disaster. So on a test, if I give you a problem like this and you start doing it this way, that is a huge mistake on the test because you're wasting time and you're not utilizing this very important theorem. Now there were some conditions. I mean, we had to have some conditions for this theorem to work. C was a smooth curve, right? Smooth meant what? The derivative. What did it mean for curve to be? Yeah, that's right. Derivative could not be 0, right? The points couldn't be 0, except at possibly endpoints. Go back and look at the definition of smooth from earlier in the class. Basically, the curve was differentiable and nice, and if we draw it, it didn't have any cusps or corners. And that the gradient was continuous. Well, the gradient was 2x, 2y. That's a nice, each component was continuous, right? They're both little linear expressions. So we had the conditions necessary. All right, now the next theorem, path independence. All right, so we have a closed curve right there. Curve starts at A, goes somewhere, comes back to itself. So the starting point and the initial point and the terminal point are the same point. When we have that, we call it a closed curve. The line integral over C of f dot dr is path independent. What does path independent mean? It doesn't matter what path, you get the same answer either way, right? Now we know, we just saw in the previous note that if that's the gradient vector field, that it is path independent, right? Doesn't matter. But if it's just an arbitrary vector field, how can we tell if it's path independent? Well, it's only path independent if and only if this is equal to 0 for every closed curve or closed path C in the domain. Which is is really not helpful. This theorem is not helpful for us because it's hard for us to use it. In order for me to tell you whether or not I have path independence for an arbitrary vector function, I have to be able to test every single closed curve and verify that on every curve I can possibly draw that's closed, I get 0 as a result. Never going to happen, right? You can't test every closed curve. It's impossible. However, we saw that if f was a conservative vector field, in other words, it was a gradient, that the answer was just the endpoints, right? Subtracted. But if you're on a closed curve, your starting point and endpoint are the same points, right? So that has to be 0, which means that line integrals on closed paths of conservative vector fields are path independent. All right. How can we then, if that doesn't work, if it's hard for us to figure out path independence for arbitrary vector fields, is there a way I can figure out if the vector field is conservative? Because if it's conservative, then I have path independence, right? So maybe there's a way I can figure out conservative pretty easily. We establish now the conditions needed for f to be conservative. Let f be a two-dimensional vector field, not a three-dimensional vector field, two-dimensional. This works for two-dimensional vector fields. For 3D, we're going to have to do something else, and it'll come later. But if we have a two-dimensional vector field, and we have a simply connected region. Oh, I didn't look at what simply connected is. This region, I'm talking about the part shaded inside there, is a simply connected region. This one is not. What's the difference between the two? The not simply connected one looks like it has a hole in it, right? The way we define it, so maybe it'll make a little more sense to you, is imagine that I have this. I'm saying this is simply connected, right? If I draw any closed curve in here, any closed curve, doesn't matter how I draw it, can I shrink that curve all the way down into where it'll just pinch off to a single point? And as I shrink it, will it always still be inside that region? Yes? As I shrink that down? Topology, you'll talk more about this. What about this region here, where I take out a hole? If I take this closed curve, can I shrink that down to a point? Yes? And still stay inside my region? But that has to hold for every closed curve I draw. So what if I draw this one? Can I shrink that closed curve down on itself and stay inside my region? No, as I shrink it down, what happens? I'm stuck around that. That hole stops me from shrinking down. So simply connected region means that basically every closed curve in it can be shrunk down without breaking out of the region itself. That's a very loose way of describing it. But so going back to this note here, it says if we have a vector field, two-dimensional vector field on a simply connected region, which all of our regions are going to be simply connected, so we don't have to worry too much about it. Suppose P and Q have continuous first-order partial derivatives. So that means that we can take the derivative of the first component and second component. Those derivatives exist. If the partial of P with respect to Y, that's the first one with respect to Y, equals the partial of Q with respect to X, if those are equal, we're guaranteed that F is conservative. That's the check right there. That's what we do to check if a vector field is conservative. So is this conservative or not? If I give you this vector field, is that conservative? So what are you going to check? Yeah, we're going to call this P, we're going to call this Q, right? I'm going to check to see, question, is the partial of P with respect to Y equal to the partial of Q with respect to X? Is it or is it not? Okay, so partial of P with, what's partial of P with respect to Y? 2X. What's the partial of Q with respect to X? 2X. Those are the same? Yes. Yes. Y is what? P, you mean partial P with respect to X equals partial of Q with respect to Y? That's the check? Well, then you're asking where that theorem comes from, which means I'd have to go through the proof of the theorem itself. Let me see if the book does. It won't work the other way, is what I'm telling you. But let me see if it does. If not, we can sit down in my office and we can go through it. It does not have the proof. However, the back of the book might. Okay? So it's a theorem, it's just presented, you take it on faith, but it will not work the other way around. It's on page 777. It's theorem 6. Actually, yeah. What? Yeah. That's all it is, theorem 6. It doesn't have a name for it. What? Exactness? Well, that's a different application of the same. It turns out to be the same check, but it's a different. You're talking about differential equations? Yes, it's same sort of idea here in a different aspect of math. Yeah. For here, we're just checking for conservative vector field. That's it. So it's conservative, right? Big friggin' deal. What does this mean? What this means is this. We know that F, right? By saying it's conservative, we know that F is the gradient of something, right? That F is the gradient of something. Does it tell us what it is the gradient of, though? Does it give us what F is? We know it comes from the gradient of something, but we don't know what that is, do we? So let me try and explain what I'm getting at here. Let's say right now you're trying to find the line integral over C of this vector field f dot dr, right? Let's say I'm asking you to do that, and I give you some, I forgot my r vector. Let's say, whoa. So I give you some curve, right? And I want you to find this. Well, we could go through the whole process, right? Figure out what f is, dot it, do all that. But we know the fundamental theorem of line integrals can make this extremely easy for us, right? But the thing that we need to have is we need to make sure that this vector field is the gradient of something, right? Now, we just checked, and it is, isn't it? So, since it is the gradient of something, I know that the answer to this will be that f evaluated at the endpoints, right? Yes or no? Okay. So even though this check is good, I still would need what in order to use this theorem? I still need the function, right? See, again, I'm saying, let's say I gave you this in the beginning of the problem. That I gave you the vector field, and I gave you the path, I gave you the r, and said, find that. Well, you go check real quick, say, oh, well, hey, hold on. It's conservative, so I know that's a gradient of something. Therefore, it's just this answer. You still need f, don't you? So the question is, how do we get f? And that's what the next part is. That's everything I just basically said. Recall from 13.1, f is a conservative vector field if there exists a scalar function f such that the gradient of f is capital F. In such case, little f is called the potential function. It's the thing that created the gradient vector. It's the thing that created the vector field. We now learn how to find potential functions, if it exists. So if you have a potential function, which in this problem we just did, we know we do, right? Because it's conservative. To do this, we're going to have to use something called partial integration. We've done partial derivatives, right? What we're going to do now is called partial integration. It's doing integrals kind of backwards, but partially. All right. Same question. Is this conservative? If so, find its potential function. So is it conservative is the first question. Is it conservative? How are you going to check? Well, f is this, 1 plus 2xy plus natural log x, then x squared. How do I check if that's conservative? Right, call that P, call that Q. I'm checking to see if partial P with respect to y equals partial Q with respect to x. What's the partial P with respect to y? 2x. What's the partial Q with respect to x? 2x. So isn't that nice? So it is, right? The answer is yes. That means that this capital F vector field is the gradient of some little f. So it has a potential function. We have to go find it now. So here we go. You ready? All right. What I know right now is that capital F is the gradient of little f, which means that our function 1, or our vector function, 1 plus 2x plus natural log x, x squared, I know that this piece right here is the partial of f with respect to x, and this right here is the partial of f with respect to y. Do you agree with that? I don't know what little f is yet, but I know that this part came from taking the partial of that little f with respect to x. And this came from taking the partial of little f with respect to y. Yay or nay? Yay? Okay. So what I'm going to do now is I'm going to write down, just start with one of those. Partial of f with respect to x is equal to 1 plus 2xy plus natural log x. What I'd like to do now is I'd like to go backwards from this partial derivative back to where it came from. So I need to integrate this side with respect to what? X, and then integrate this side with respect to x also. So I'm going to come in here now, do the integral of the partial of f with respect to x here with respect to x. And then over here, integral of 1 plus 2xy plus natural log x with respect to x. Now on the left side, what do I get? Little f, right? Little f, which is what we're trying to find, isn't it? Now on the right side, I integrate this term by term with respect to x, treating y like a constant. So this is kind of like the double integrals, triple integrals we did, where we're integrating like on the inner one, and we would just be treating y like constant or x. So what's the antiderivative of 1 with respect to x? X, antiderivative of 2xy with respect to x. X squared y, antiderivative of natural log x. X ln x minus x. That's one that you may or may not have been drilled into you. I don't know. Depends on how your calculus instructor was, but everyone knows the derivative of natural log of x is 1 over x, but not many people remember the antiderivative of natural log of x is this. Yeah, we're not done yet. Okay? So now, when we do integration, we usually have a constant, right? Plus c. However, because we did partial derivative, right? When we were up here, when we took the partial with respect to x and got this right here, that thing that was out here, right, that we took the derivative of, right, with respect to x, let me go back there. That answer up there, which is this, is what happened when we took the derivative of little f with respect to x, which means anything that just had y in it, just y, would have gone to what? 0, right? So when I say plus c, I'm not saying it had to be a constant, right? It could have been a constant, but it also could have had just y's in it. So instead of saying plus c, I say this, plus, and I'll use g since we're not using f, since we're already using f, plus g of y, meaning this right here could have been any function of just y. Could have been sine y, could have been y squared, y cubed, anything, right? Could have been 2 plus y cubed. Or it could have just been 4. But it's not a constant, so to speak. With me? All right. So what we have right now is we have little f within a function. We're close, but we're missing a function here. We don't know what this is. So the way we're going to get this is now we're going to come in here and we're going to take the derivative of this with respect to y. What's the derivative of that with respect to y? Don't worry about what's up there yet. But what is the derivative of this with respect to y? So derivative of this one right here would be 0, right? Derivative of this piece right here would be what? X squared, right? Because y is our variable. Derivative of all of this would be what? 0. And then derivative of this would be what? G prime of y. Wouldn't it? G prime of y. Now, I can say either G prime of y, or I'll do it over here. I'm out of room. Can I go to the next page? I have partial f with respect to y is equal to, we said, x squared plus, I said G prime of y, or you could put this, G sub y, right? That's the same thing. That's like the derivative of G with respect to y. Now that is what the derivative of little f is with respect to y. But don't we already know what that's supposed to be? Don't we? Go back up here. We know that that's supposed to be x squared, isn't it? So if I go back to this, I say, but fy must be equal to x squared. Therefore, x squared plus g, partial g with respect to y, must equal x squared, right? Those have to be equal to each other. Which means what? Partial g with respect to y must be 0. The partial of g with respect to y must be 0. So now what? Go back over here. F was what? This plus this plus this plus g of y, not partial g with respect to y, g of y, or just g, right? What I know right now is that g, partial of g with respect to y, is 0. I need to know what g is, not the partial g with respect to y. So how do I get g? Integrate that with respect to y. So if I integrate this with respect to y, and then the other side, integrate 0 with respect to y, well, what's the antiderivative of g with respect to y with respect to y? That's just g. And then over here, what's the antiderivative of 0? A constant. Now, why do I know that there's not an x in here? I already dealt with that up here. Well, not up here, but back here, I said that this right here was a function of y only. I said x couldn't be in here, right? So that's a constant. So my answer, final answer, is that little f was x squared What was it? Was it x squared y? Wait a minute. Oh, x plus. Did I do a different problem than was on the... Oh, x squared y plus x. Oh, these x's cancel. Sorry. I'm looking at the answer I came up with a while back. Okay, those x's cancel. See those? Okay. I was like looking and going, what the hell? So f is equal to x squared y plus x ln x plus some constant. That is my family of potential functions. I could replace c with any number, and that would create that vector field when I took its gradient. Make sense? So if we have this problem now, if f is this vector field, find the line integral over the vector field, right? So f dr, where c is given by this right here. Then you could go through a long, tedious process of trying to figure out what f dot dr is and trying to, put that all together. Or you could just use what we just figured out. We know the potential function, right? We know little f. We know little f, so we could evaluate that. We'll make that what we're going to do at the end of class. We'll do that, okay? Let's look at this last example for this section. Oh, man. Where'd you go? What the hell? All right, we have not seen what it takes to show a vector field in three-dimensional space is conservative. All right? What do we do to see if a vector field is conservative in two-dimensional space? Yeah, you do the partial p with respect to y, partial q with respect to x. You check that they're equal. If they are, you know that it's conservative, right? I'm going to wave my hands right now. Later on, we'll do this. We don't know how to do it for 3D yet. But let's assume, just for this example, that we know that this is a conservative vector field. Let's assume that we know that. Then, in order to use the fundamental theorem of line integrals to compute a line integral, I need to know what little f is, which means I need to be able to figure out what this potential function, what the potential function is for that vector field. It's a three-dimensional vector field, though. But we use the same process, partial integration. But it's much more complicated here. All right, so let's go through this one. You ready? Let's say we have our vector field, x squared plus 3z squared. I need to now try and find little f, right? That's my goal. Find little f. What do I know? I know this piece is the partial of f with respect to x. I know this piece is the partial of f with respect to y. I know this piece is the partial of f with respect to z, don't I? I know those three things. So just like before, I'm going to pick the first one. I'm going to go partial of f with respect to x. I know what that is. It's 2xz plus y squared. So now from that one piece of information, I'm going to go backwards to try and get little f. So I'm going to do the integral with respect to what on both sides? With respect to x, right? So I take the integral with respect to x on the left, integral with respect to x on the right. What do I get on the left side? little f. On the right side, x squared z plus y squared x plus well, my little f was allowed to have what variables in it? My little f is a function, right? It could have what variables in it? X, y, and z this time, right? And anything that had x's, I would have to worry about when I took the derivative and got this, right? But anything that had just y's and just z's in it would have all gone to 0, wouldn't they? So what I'm going to say out here is instead of a constant, I can't use constant, I'm not going to say g of y like I did in the previous problem because I also have z's. So I'm going to say g of yz. Whatever's out here could be a function of two variables, but just y and z. With me? See, this is the most important part of this partial integration, is understanding that your constant of integration is no longer a constant. It is actually a function of integration. And the other variables that aren't there are the ones that appear in that function. All right, now what? So now what we do is we take that, we work with that, and we differentiate it with respect to y now. Right? Take derivative of that with respect to y. What do you get? So derivative of this first one is 0, right? Derivative of this one, 2yx, 2xy, doesn't matter, right? With respect to y. And then what about this one? What's the derivative of g of yz with respect to y? It's a derivative of g with respect to y, isn't it? So I'm going to write derivative of g with respect to y. You see why I'm not going to write g prime of y or something like that? Because I have z in here also. So this is technically the right way for me to write the derivative of g with respect to only y. Okay, what do we do with this? Compare it to what we had up top. What did we have up top? We know that that has to be equal to what? From up here, 2xy? Right? What does that mean? That means that g sub y, right, g of y, the partial, must be 0. Is that enough for you to tell me now what g is? Well, we can integrate that now, right? So we integrate g with respect to y, with respect to what variable? Respect to y, and we get the integral of 0 with respect to y, which is, what's the left side? G, and that must equal what? Could have z in it, right? Because look, we said the derivative of g with respect to y must be 0. But what if g had z's in it? Then those would have gone to 0, wouldn't they have? So it is possible that because g had y's and z's, that when we took this derivative and got 0, we still could have had z's in there. So when we integrate this side right here, we could have what? Some function of z, right? So I'm going to use h of z. I could have some function of z here, which could turn out to be a constant, but no matter what, it has just z's in it. Because when I differentiate it, right, when I differentiate it, it has to go to 0 when I differentiate with respect to y. All right, so let me go back up. Where the hell am I? Go back up to f. Where are we with f? Let's do a little spot check here. We have x squared z, right, plus y squared x plus g of yz, right? But what is g of yz? Well, this is what g is now, right? So I know that g of yz is actually just what? Some function of h. So I'm sorry, some function of h, some function of z. Now the only reason that this is turning out so freaking nice is because at this step right here, this has been 0, right? Do you think on your take-home exam that's going to be 0? No, it's not going to be 0. Which means that when you integrate both sides here, you can get something a little more complicated. But the technique is still the same, all right? Now what? This is where we are. Take the derivative of that with respect to z now. So what is the partial of f with respect to z? Well, x squared plus the derivative of that with respect to z, right? Is the only thing left. So how about h sub z? I don't really need, technically I could put h prime of z here because it only depends on z, but I'll still use the same notation. But that has to match what? What does that have to match? Up from the top, x squared plus 3z squared. Oh, okay, finally one that doesn't have 0 in it, right? That has to match what we had from up top, which means that the partial of h with respect to z must be what? 3z squared. So the partial of h with respect to z must be 3z squared. When I integrate both sides there, right? Integrate the left, integrate the right, with respect to what? Z on both sides. I get h is what? Z cubed. It's all right. Don't have to apologize. Plus c. Plus c. This time I can say it's a constant. Right? I can say it's a constant. Because h was a function of only z, I know that when I get my h, it should only have z in it and possibly a constant. So let me do my last rendition of f. Here's f, right? My final version of f is, trying to get it all on one page, f is equal to x squared z plus y squared x plus z cubed plus a constant. Now what's the good news about these problems? What's the good news? Yeah, that's true. How do you know if you're right? Take the gradient, right? If I take the gradient of that, the gradient vector field, it should match what I had up there, right? If it doesn't, you messed up somewhere, right? So there's a way to check your work pretty easily. Let's just check it. What's the partial of this with respect to x? 2xz y squared. Is that what we had? Partial of this with respect to y? 2xy. Is that what we had? Partial of this with respect to z? X squared plus 3z squared. Okay, it checks. See? What do y'all think? All right, we're done with this section. 749. Do what? You don't need what? Oh, before you leave, you mean? Is that what you're talking about? Let me give you make sure I've got the homework correct here for both these sections. For 13.2, I don't know what page it's on, but there is a modification on this homework. It's not exactly what appeared in your notes. What, are you implying you're ready to go or what? 1 through 13 odd, 19 through 22, and then for 13.3, (3 through 15 odd. Wow, we're going to start Green's theorem next week. Nice. Okay, so look, I will spare you the other assignment, but let's do it this way. That example 7 that I was going to have you do right now, that's going to be, was it example 7 or was it? Which one? That one? Oh, example 4, you're right. No, that's like a 5-minute problem. No, we found little f. In the previous example, we found little f, right? All you have to do is figure out what the endpoints of the interval are, or the endpoints of your curve, plug in, you're done. I mean, that's kind of like the grand finale of that. Like we had set it up, example 3 was all the work that we had to do. Well, no. Yeah, example 3 was all the work. Okay, I tell you what, I'll let you go, but you better have that for me to turn in on Monday, okay? First thing, have it on my desk.
I don't care if I leave. I want to know.
I'm going to go to my office, though. I'm still recording. I better turn that off. Everybody.